Hello everybody, my name is Yevhen Kuznetsov and I am presenting CoMoDA, a fast and simple method for continuous depth adaptation. Most self-supervised monocular depth estimation works assume their models fixed after the training is finished. Such an assumption does not allow to adapt a model to new scenes. On the other hand, these models can be optimized without extra annotations using a video recorded by a moving agent, also at test time. Recently, several works leveraged self-supervision to higher extent by doing test time fine-tuning. They perform multiple backpropagation iterations to optimize a pre-trained model on a frame triplet from a test video. However, the model parameters are reset for every new frame, thus forgetting everything learned after training. We, by contrast, propose to adapt the model parameters on the fly on test videos continuously, without reset. Since the environment normally changes gradually in videos, our method benefits from the recently learned information, requiring only one backpropagation per frame. This results in a dramatic speedup compared to test time fine-tuning on isolated frame triplets. Given the pre-trained depth and ego motion estimators, the baseline adaptation works as follows. The depth maps for the first two frames of the test video are predicted without any model updates. As soon as a new frame is acquired by a camera, camera motion is estimated between the previous frame and its neighbors. Then, if the camera translation is sufficient, we synthesize the previous frame using the neighboring frames and update the model to minimize the difference between the synthesized and real images. After the optimization, the depth map for the current frame is estimated and the described procedure is performed for every following frame until the end of the video or stream. Unfortunately, in our experiments, we observed that our baseline sometimes demonstrates degraded accuracy compared to the non-adapted model. We noticed that this often happens when the appearance of the environment in a video changes rapidly. For instance, when a car is turning, as in this example. During adaptation, the model is supervised with many consecutive video frames. These frames look very similar most of the time, and the corresponding supervisory signal can cause the model to overfit to short video segments, leading to worse performance when the scenery changes. In order to overcome this issue, we introduce experience replay as a crucial element of monocular depth adaptation, augmenting the supervisory signal of the baseline with the experience from the distant past. In particular, in addition to optimizing the model on a triplet of consecutive images from a test video, we use one or several triplets randomly drawn from the replay buffer with the data previously observed by the model, for instance during pre-training. The use of experience replay prevents the model from overfitting and effectively stabilizes the adaptation procedure. In this slide we show the results for transferring from train to test set of Kitty. You can see the performance of CoMoDA compared to the non-adapted model and the baseline adaptation without experience replay. CoMoDA improves over the non-adapted model almost on every test video, and the videos show an example of how the model evolves during adaptation. We also show the results when transferring from Kitty to new scenes. The relative improvement over the non-adapted model is even higher in this setup. Note that due to the big gap between the scene appearance in these datasets, the baseline adaptation outperforms the non-adapted model. Nonetheless, the use of experience replay still brings a substantial accuracy gain. As you can see, CoMoDA demonstrates state-of-the-art performance surpassing not only the methods not performing test-time model updates, but also struct2depth and GLNet. Moreover, our method is orders of magnitude faster compared to the competing test-time fine-tuning approaches. To conclude, our work clearly shows the benefits of continuous depth adaptation. Yet, there is still much room for improvement. The possible directions to explore are handling of moving objects, which is crucial for monocular depth adaptation, strategies for experience replay, or even the use of other regularizations, or strengthening temporal consistency with RNNs. If you are interested in the implementation of CoMoDA, please visit our GitHub repository. Thank you for attention.